Good evening, Panindra. I will just admit some more participants and then I will begin the session. Okay, so uh, before we begin, all I want to say is that uh, my name is Rachit Verma. For those of you who haven't met me, and I am a PhD student at IIT Dharwad, and I will be serving as the TA of Foundations of Cloud IoT Edge ML. Uh, so now the professor responsible for this. Just a second. Yes. So the professor who has conducted this course, his name is Professor Rajiv Mishra. I'll be serving as the NPTEL TA for this week's problem session. If you want to contact me, you can contact me at rachitvarma.ea@gmail.com if you have any doubts or anything along those lines. So before I begin, I will briefly go over how this session will be conducted. So I will first summarize to some extent what was previously discussed in the last two lectures, or in the lectures corresponding to this week, and then I will go over some of previous year's assignment questions that were some previous year's assignment questions, as in the last time this course was offered. After which I will go into the question and answers that I have formulated for you all to help you practice for the assignments and for the final examination to gain a certificate for this course. Before we begin, I would like to say this recording of this session will be uploaded to YouTube. So if you're not comfortable with showing your video, please don't enable video. And I would like to make this session as interactive as possible. So I'll be asking you questions, and it would be very helpful for me if you also respond to those questions as well. So let's begin. So 2 lectures were conducted. So the first lecture was enabling intelligence at the edge layer of IoT, and in this lecture you discussed what were the issues in the traditional IoT platform, how Edge ML addressed the issues of the IoT platform, the workflow of edge machine learning, and the advantages and the applications of edge machine learning. So there were and then while these were like the general outline of what was discussed, we also saw a real life example of how machine learning on the edge could be conducted on the Azure Web Services platform. We saw how Azure IoT Hub could be used to enable machine learning on the edge, and we saw that the entire workflow for a video camera. We saw the entire workflow for enabling this. So, for example, we saw the creation of a workload description, a deployment manifest, and we saw the container registry. We saw how the code that you create can be put into the container registry to be installed on the edge, and we saw how this effectively creates a software as a service. And then after that, so these were the main takeaways. And then in addition to that, we had also revised what training was and inference was. This was also like previously discussed in the previous lectures, and we saw what the pipeline of creating machine learning model is on the edge. And then after that, in the second lecture of this in the second lecture of this series, we discussed some very specific a very specific case of computer vision. So if you are unaware that machine learning need not happen only in the case of computer vision, machine learning can also happen if the data has the form of a text, if the data is in the form of time series, and if the data has other shapes as well. So very specifically for the case of object detection, some machine learning models were discussed, and we saw a certain practical application of this machine learning in the case of of a Raspberry Pi as well. So So the models that we discussed was RCNN, fast RCNN, faster RCNN, single shot detector, and a YOLO detector. And we also saw the various kinds of different techniques in computer vision, which included image classification, detection, segmentation, and we saw the basics of computer vision and machine learning. We saw how computer vision, how Azure Compute Vision, which is a software as a service, could be used to enable custom vision. Azure Custom Vision could be used to enable the uh, enable creating computer vision models without actually writing any code, or without writing any code. So in which you can just upload your data, and we saw how you could modify the performance thresholds depending on whatever thresholds are relevant to you. Okay, so now this serves as a I think I think we have roughly summarized what was discussed in the previous lectures, and okay, I think we can go ahead with the question answer sessions now. Okay, so I'm sorry. So list out. So the first question is list out the limitations of the traditional IoT platform. Is it A, poor internet connectivity? Is it B, poor data gravity? Is it C, poor real time responses? Or is it D, all of the above?
All of the above.
All of the above.
Okay, yeah, so this is correct. So the all of these are definitely limitations of the IoT platform, or traditional IoT platform. So let's say you had a so for those of you for whom this is not clear, um, so if uh, in the event that there is poor internet connectivity between the IoT and the cloud, you cannot really do any intelligence enabled actions or insights, because you don't have connection to the main server. But in the modern IoT platform, like even if you don't have internet, you can use some local protocols, local network. You can use some other connectivity techniques to connect to a nearby edge device and actually handle and actually get the insights and the actions from them. And poor data gravity, because if you poor data gravity is that scenario when you have a huge amount of data which is being flooded to the cloud, so that can kind of congest the network channel. Poor real time responses, we have already discussed this very frequently in the context of the round trip time. If there's a huge amount of round trip time, you may get a poor real time responses. Dash is the edge computing approach that significantly saves the bandwidth and cloud storage. Is it A, filtered data transfer, B, faster decision making, C, both of them, or D, none of them?
C. Both of them.
No, no, no. I want you to think about this carefully, right?
A.
Yes, yes. Thank you, Abhiru. Okay, so there is some confusion between A and C. So, so faster decision making isn't exactly an edge approach. So uh, that significantly saves the bandwidth and cloud storage. So if you make the decision faster, right? Let's say on the edge, because let's say a GPU or a CPU. Uh, now, now that isn't exactly going to save the bandwidth or the cloud storage in any way, right? Because the data is not exactly being what are the fundamental characteristics that affect the bandwidth, right? So if you're sending a lot of data, so that may affect the bandwidth, and if you're sending a lot of data, that may affect the cloud storage, right? So if you make decisions faster, you're not really affecting the data in any way. But if you filter the data that you want to transfer, right? If you if you filter if the data that you want to send to the cloud is filtered at the edge, because let's say you are able to do some sort of inferencing at the edge, what that will do is it will reduce the bandwidth and the cloud storage. And of course, none of them is not the answer, because we have filtered data transfer as the right answer.
Yeah, yeah, filter data transfer.
Okay, thank you. So in the inferencing phase, a developer feeds their model a curated data set so that it can learn everything it needs to about the data it will analyze. Then in the model shifting phase, the model can make predictions based on live data and produce actionable results. The statement is true or false?
False.
False. Okay. Any other responses? Okay. Okay, fine. So I think there are no more responses other than this. So if you analyze the sentence, right? A developer in the dash phase, a developer feeds their model a curated data set so that it can learn everything. So the inference phase actually happens after after the model has already learned everything, right? So it does not happen. Uh, just a second. Stay there. Okay. So the inference phase is what happens after a model has already learned from training, right? So after it's, let's say you are writing an exam, you have already studied everything, so now you go to the exam to write the answer. So that is the inferencing phase. And the model shifting phase is something that is not discussed, and it is right now it is meaningless. But we say over here the model can make predictions based on live data to produce actionable results. So after the model has been trained, it can now ingest some data from it can now like ingest some data from various places. It can now ingest some data from various places, and based on the insights that it has learned during training, it can give some actual result, right? So that is what inferencing means. So if you wanted the statement to be true, what you would do is you would say in the training phase a developer feeds their model, whereas in the inferencing phase the model can make predictions based on live data. Okay, I hope that's clear.
What is model shifting phase? Is
It's
this deployment phase at the edge or something?
it doesn't mean anything actually. To be honest, it was there in one of the options. Okay, it does not mean anything. I've just modified like last year's assignment. Okay, like
Okay. So nothing to know.
yeah. I mean, if you probably go into like some sort of very complex machine learning environment, it may mean something, but for this case, it does not. Okay. So dash involves calculating explicit label for every data point in the sample based on the actual observations on the data. So is it A, data preparation, B, data collection, C, data streaming, or D, none of the above? Any responses? Yeah, okay.
A.
Yeah, okay, that's good. So A data preparation involves calculating explicit label. So if you look at the entire machine learning pipeline, what you'll do is you'll first prepare the data, you feed it for training, and you'll do inferencing. So the kind of machine learning that you have kind of come across is called supervised learning. So in supervised learning, you need that explicit label. So for example, if you let's say give me an image of a cat, the model needs to know that it is a cat, so that it can learn what it means for an image to have the pixels of a cat. So this phase comes under data preparation, and and it involves giving an explicit label. So list out the key characteristics of Azure IoT Hub. That's it. A, managed service for bidirectional communication? Is it B, platform as a service, or does it C, or is C, programmable SDK? Is it D, all of the above?
It's all of the above.
Okay, any other responses? Okay, fine. So yes, so it is D. Sorry, D. Okay, so yes, so it is D. All of the above. Um, so now why is it D? So if you have two devices which are in the which have been provisioned in the IoT hub, right? So you can handle uh, like these two devices can communicate between each other. So we can say that it manages service for bidirectional communication. Now it is a platform as a service, and it also provides a programmable SDK, right, for devices in this platform. So which of the following studies various techniques to classify patterns? This is very easy: image processing, photogrammetry, image recognition, or pattern recognition. Any responses?
Image processing.
Sorry.
D.
D. Okay, yeah. So it is correct. So D is the correct answer. Pattern recognition. So image processing and image recognition, these are definitely valid fields that you could that could involve pattern, but it is not general pattern recognition, right? These are like very specific for images, and photogrammetry I am honestly not fully sure what it is, so I'll skip it. So the input and output of image processing are A, the signal and the image, and B, the signal only, C, image only, or D, depends on input. So I don't know if this has been
C.
covered in the lectures, but this was there in previous year's assignments. Uh,
C.
See, okay, so this is not really necessary, right? So I don't know if you have any experience in image processing, but you know, images you can take an input, you can take an image, you can compute a Fourier transform on it, right? So you can treat an image as a signal. So these kind of transformations are possible on images as well. Uh, so it need not necessarily always be you take an image, you get some kind of output. So you can take like the frequency representation of a frequency domain representation of an image, and you can bring it to the time domain. So all sorts of things are possible. So that's why the answer is it depends on the input. Okay.
Okay, got it.
So in fast RCNN, we extract feature maps from the input image several times as compared to RCNN, where we extract feature maps from each region proposal separately. Is it true or false?
True.
Any other responses? Fast RCNN. I don't know if you all remember that. Fast RCNN. And there's traditional RCNN and there's fast RCNN. Is it A true? Okay, so
No.
no. So the answer to this question is actually false. So I don't know. So if you remember so if you remember uh, in the lectures, right? What happened in fast RCNN was you would pass an image through the convolutional neural network, and then it would generate then some feature maps. At the end of the last feature map, you would use some sort of region proposal finding algorithm, right? So you would take only that one final feature map and generate the region proposals. Okay, and whereas in RCNN, what we actually did was we took an image, we generated the region proposals using selective search. Each of those region proposals were passed through a convolutional neural network and which were then either classified or regressed using classified into various classes of images using a support vector machine, or using linear regression we found the bounding boxes. So I hope this is clear. So the answer is actually false. We only find the feature map once in the case of fast RCNN. Which of the following networks has the fastest prediction time? RCNN, fast RCNN, faster RCNN.
C.
C. Okay. Yes, faster RCNN. So, any other responses? Okay, C. Fine. So this you can infer directly from the name, but you should have like a deeper idea of why this is true. So the RCNN we create, as I had just discussed, we created region proposals for every. We created region proposals from the image itself, and you had multiple convolutional neural networks. Fast RCNN, you had only one convolutional neural network that created a feature map on which we found the region proposals and did the bounding boxes. Faster RCNN, we instead of using some sort of selective search algorithm, we used what we did was uh, we created some anchor boxes for after sliding a convolutional after creating a sliding window on the feature map, on the final feature map. So this was called a region proposal network. So instead of using some sort of selective search algorithm, we created some anchor boxes based on a sliding window that was passed through the last layer of the feature map. Okay, and this was passed to the region ROI pooling layer, and then a network was used. So list out the features provided by the Azure Custom Vision Service. A. Train a computer vision model by simply uploading and labeling few images. Is it B. Build image classifier model using code-free and code-first approach. Or is it C. Deploy the model in the cloud, on-premise or on-edge services. Or is it D. All of the above?
D.
Huh? Okay, any other responses? Okay, so yes, so D is the correct answer. So if you can train a computer vision model by simply uploading and labeling few images, and you don't have to do any manual coding, and the model can be deployed the cloud, on premise or on the edge devices. That is true. So now I'll go over these were the previous year assignment questions. Now I'll be going over some multiple choice questions that I have created for you. So what is the primary concern related to the functionality of an internet dependent fire alarm in the context of IoT? Is it A. Power failure? Is it B. System malfunction? C. Poor internet connection? Or D. Lack of sensors? In the context of IoT, so the most appropriate answer is what I'm looking for.
C.
Okay. C. Any other responses? C. Okay, fine. So this was somewhat discussed in the lectures as well. So in the context of IoT, right? So what we are discussing, so power failure, system malfunction, lack of sensor. So if you look at the architecture, so we're not really discussing this, right? It's only in the context of a poor internet connection this can be somewhat painful, because when we say an internet dependent fire alarm, we already have a fire alarm in place, right? And that is like somewhat functioning. So those are like outside the scope of, those other three options are outside the scope of the discussion. So what is the text, why does the text mention data gravity in the context of IoT devices? Is it A, to highlight the sheer amount of data generated by IoT devices, B, to emphasize the need for cloud storage, to explain the concept of data streaming, to describe the efficiency of data processing?
Option D.
Option D, to describe the efficiency of data processing. Any other responses? Hmm?
Option C.
Option C. So, no, no, no. So, data gravity may be, the term may be
B.
used in these contexts. Okay, but fundamentally, why is it, what does it mean, right? That's what I'm looking for. So, so,
A.
sorry? A. Okay, okay. Yeah, yeah, okay. Thank you. So fundamentally, what does the data gravity term imply, right? So gravity, like mass. So what is it that's creating mass in terms of data? So like there's a huge amount that's being streamed, right? So that is what is creating.
Yes.
Yes. So there's a huge amount of data that is being streamed. So that is what is creating the data gravity. So so in that sense,
A,
yes,
A can be answered.
yes, yes. Okay. So in that sense, uh, so what do you say? Yeah. So so in that sense, A is the right answer because we want to highlight the sheer amount of data that is being generated by the IoT device, and so now this may imply the need for cloud storage. Okay, uh, but fundamentally, what we want to do is we want to take this data that is amount that is being generated, and we want to reduce the amount that is being sent to the cloud either by the edge or through some other means. Okay. So what example is given to illustrate the need for local processing on IoT devices? Is it streaming videos constantly, continuous data shipping to the cloud, identifying faces on a smart doorbell, uploading data to a central server? So now this
Option
is,
C.
yes, yes. So now any other responses? So more than that, I am also interested in like why this
It's C.
example. Yes. Okay. So thank you. So more than what was being given in the text, I am more interested in understanding like why this example was given. So just a second. Just a second. There's a problem with the recording, I think. Okay, fine, fine. So, uh, so what examples? Okay, so why was this? So why has this example been given? So specifically, if you think about it, uh, if you have a smart doorbell, you want to do first the object detection on it, and then you want to do image classification on it. So this can be somewhat challenging if every time you have to send this huge amount of image data to the cloud. So if you're not aware of this, so image data is actually very heavy, right? So any kind of image that you have, it has a lot of detail in it, and sending it to the cloud and sending it back can be like somewhat like very challenging at times. So that is why So that is why, this example was given. Continuous data shipping to the cloud, so that is not necessarily always very intensive, but this streaming videos constantly does not, we have not really identified a certain like what certain processing, like this has not really been discussed in this part A, so it is not the right answer. And D is pretty general. Okay, so what is the consequence of internet outages on actions dependent upon cloud computation of IoT devices? Is it A, improved accessibility, B, uninterrupted operations, C, inaccessible insights or actions, or D, enhanced cloud connectivity? Any responses?
C.
Yeah, that is true. So basically, these IoT devices depend on the internet for receiving the insights and the actions. So um, which is why we actually require this internet connection. The other three are actually improvements in the so the other three options are actually improvements in the IoT. So that is why they're not relevant. So, what term is used to describe the issue where too much data is overwhelmed into the cloud and devices are heavily dependent on cloud services and internet connectivity? Is it A, data gravity, B, cloud saturation, C, IoT platform bottleneck, or D, real time overload? A. Okay, any other
A.
A?
B. B.
D? So, A and D could actually both be accurate answers, but from the if you look at the context of the lectures, right, it's actually data gravity has been used in the in this context, right? So and also, uh, I think this dependence, right, heavily dependent on cloud services and internet connectivity. So this is not really exactly captured in the real time overload in that option. So
Are you telling B? B. Cloud saturation
I'm
or
saying
something?
data gravity. So in which scenarios does the issue of sending data back to the cloud become prominent in traditional IoT systems? Is it A, remote monitoring or control situations? Is it B, localized data processing? C, internet connectivity issues? Or D, data storage challenges?
Internet connectivity issues. Remote monitoring.
No.
A, remote monitoring or control situations.
Okay. So any other responses? D, data storage challenges. Okay. So, uh, so now this data storage challenges, that is not a very specific. So let's say if this was single correct, right? How would you answer it? So I think, see, when would you send data back to the cloud, right? So fundamentally, because there is some kind of inferencing that you want to do, that you are unable to do on the edge for some reason. Either that, or you want to do some kind of training that you are unable to do. That training that you are unable to do on the edge, right? That is when you would send data back to the cloud. So when is that apparent, right? You'll need some kind of scenario. So if there are like simply data storage challenges, that is pretty vague, right? So but if you consider remote monitoring or control situations, right, we need some sort of inferencing or we need some sort of training to happen, right? So in this kind of case, you would actually send data back to the cloud. But if you consider like simply like internet connectivity issues, um, internet connectivity issues may even make it impossible to send data back to the cloud, because see, it's not like the edge where you can use some sort of LoRaWAN or something like that, some sort of some sort of communication protocol to just communicate with the edge. You need internet to communicate with the cloud. Just a second. I'll be back. 1 second. I need to get my power cord. Okay. Uh, so what is a common use case for the aggregation of remote data across multiple IoT devices in traditional IoT systems? Is it
Option C.
option C? Okay. Any other options? Reducing latency in real-time responses, enhancing internet connectivity. D. Implementing near real-time processing. Or C. Training machine learning models. Any other responses? Okay, so I will explain. So the answer is okay. Rajesh Kumar has said D. Okay, fine, fine. So if you want to aggregate data across multiple IoT devices, so when would you do that, right? So if you want to implement real-time processing, you would do something very local, right? So and that also, like after all the data has been aggregated and all the processing has happened, then you would want to do some sort of inferencing that is very quick. But the thing about this aggregation of remote data across multiple IoT devices is that it is very time consuming, right, and challenging. So so because of that, you would not want to do this aggregation of remote data across multiple IoT devices when you want to do something near real time. You want to do all this aggregation beforehand. On the other hand, when it comes to training machine learning models, it is okay to take some time to do some sort of processing. Uh, it is okay if you want to take some time to do some kind of processing. So and also it requires, and also in the case of training machine learning models, if you, let's say, only train from one single IoT device, your model may not be that very efficient. So in that case, you will want to take a lot of data from many IoT devices and do some sort of training. Or if you do go into federated learning, you will see a much better, something much better than this. Let's wait for that lecture to come. And so we, of course, aggregation of remote data across multiple IoT devices does not enhance internet connectivity in any way. In fact, you need internet connectivity to enable the aggregation of data, and it does not reduce latency unless you bring, let's say, the device closer, or you do something in the realm of hardware. Exactly, that's the only way to reduce latency. So for example, edge, you kind of bring some computation close to the end device, right? So that is some kind of hardware thing. So this is this software. So why does the traditional IoT system face challenges in providing near real-time responses in remote monitoring or control situations? Is it A, inadequate data storage, B, delayed runtime, C, overwhelmed data in the cloud, or D, dependence on cloud services?
D.
Okay,
D.
sorry, D. So D is
Option B.
sorry, B. Yes, so I can say that there is some kind of confusion between B and D. So yes, so if you were to do, let's say, multi-correct, definitely B and D would both be correct, because if you're depending too much on the cloud, then then definitely you will encounter some sort of problem with real-time response, because the cloud is generally very far away from these IoT devices. But But if you look at very closely, right? So why exactly is the cloud creating this issue? It's because of the very huge amount of round trip time. So in that sense, B, if you ask me, would be the most accurate answer. Okay, and yes, and inadequate data storage is not the right answer because the cloud generally has sufficient data storage. You can consider it as having infinite data storage. Right? It's only something like the edge or maybe some IoT device that has limited data storage. So, what is the advantage of performing machine learning on the edge in terms of response time? High latency, low latency, variable latency, no change in latency.
Higher latency.
Machine learning on the edge, low latency. Okay, so I think there was some sort of confusion over here. So we're talking about machine learning on the edge in comparison to doing it on the cloud, right? So so in comparison to the cloud, if you see, let's say you want to do some sort of inferencing, then and your let's say your IoT device is not capable of doing that inferencing very fast. So in that case, you should do it on the edge, and you'll also have like you'll have lower latency provided you have set everything up properly. In comparison to the cloud, it is definitely it has lower latency. But of course, if you can do everything on device, that will be much better as well. But most of the time, on device is not possible. Okay, so variable latency. So what is the benefit of pre-processing sensor data on premise uh, in an edge computing environment? So is it A, reduce data storage needs, B, minimize cloud dependency, C, increase latency, and D, enhance cloud processing? Dev has said B. Any other response?
D.
B. Vinay?
B.
B?
Yes, B, sir.
As in like B, second option? Or fourth option?
Yeah, second option.
Okay, fine. So yes, so that is the correct answer. Minimize cloud dependency. So why is this happening? So if the data is, let's say, already been processed on the edge, right? Then you don't need to do that much processing on the cloud. Okay, so in that case, your dependency on the cloud will reduce, and now as far as reduced data storage needs is concerned, that may not necessarily always be true. That may not necessarily be that significant in comparison to minimized cloud dependency, and increased latency. Once again, that kind of depends on the scenario. Okay, we don't really know this for sure. Also, enhanced cloud processing, that is somewhat vague. So in the updated IoT model, where are insights generated? So only at the cloud, only at the edge, both at the edge and the cloud, and neither at the edge nor the cloud, like everything on the IoT device. Okay, Vinay said B, Rajesh Kumar has said B. Any other?
C, both at the edge and cloud. C.
Okay. Fine. So I can see that there is some amount of confusion between B and C. So let's say if an insight is very challenging to generate, right? So we had already said this. So we are sending data from the edge to the cloud. Now why are we doing that? So when the edge cannot deliver, then the cloud will deliver, but at the cost of increased latency, right? So what is the edge failing to deliver? Right? It's failing to give an insight clearly. It is failing to generate an insight from the data. So in that sense, we are sending the data to the cloud for generating the relevant insights. Okay, so in that case, we say that the insights are generated both at the edge and the in the cloud. Basically, when the edge fails, cloud takes over. So, of course, that eliminates A and B, and neither at the edge and cloud is also false, because if if that was true, then you would have to generate insights at the IoT platform. But these IoT devices, like a fire alarm, right? It cannot really do that kind of computation that an edge device can, like a Raspberry Pi or something like that. So if you were to like order the devices in general in the order of increased processing power, so at the lowest would be the IoT devices, then the edge devices, then the cloud. In the cloud, you can consider as having nearly infinite processing power. So, what problem does deploying business logic at the edge layer aim to address in terms of data processing? So, is it increasing cloud storage costs, B, reducing cloud bandwidth, C, ensuring high latency, or D, handling the increasing amount of sensor data? Any responses? D?
D.
D? Okay. Okay, fine. Yes. So D is the correct answer. Uh, so deploying business logic at the edge layer. So aims to the issue that aims to address in data processing is handling the increasing amount of sensor data. So what happens is, if you increase the sensor data, if the sensor data increases very significantly, uh, so you may once again you will face the problem of data gravity. But if you have an edge layer, so this can be processed and filtered before this can be processed and filtered. And so business logic, in the sense, let's say you want to generate some insight, and then based on that insight you want to do some kind of action. So this kind of logic will be there at the edge, and you can use that, the data that is sent to the edge, to conduct this kind of to conduct all these kind of actions. So that is why business logic is deployed at the edge layer. So what is the primary advantage of sending only a subset of data to the cloud in IoT edge computing? Is it A, reducing edge storage costs, enhancing cloud processing, reducing cloud bandwidth, or D, increasing data generation at the edge? Any response? Okay, Vinay has said C, Rajesh Kumar has said B.
Option C.
Okay, so yes, so C is the correct answer. So if you send only a subset of data to the cloud, once again, what you will be doing is you won't be jamming the bandwidth. Yeah, you won't be jamming the network connection, so the network channel, and so because of that you will have a sufficient. Uh, because of that, you will be reducing the cloud bandwidth, and there's a confusion between B and C. So it does not enhance cloud processing in any way. To enhance cloud processing, you will need to install some better chips or better hardware to be able to do that. If you only send a subset of data, the only thing that will happen is you will have to process less. And as far as increasing data generation at the edge, so that is not exactly an advantage, right? The edge may do it irrespective, but that is not really an advantage of sending a subset of data, and neither is increasing data generation an advantage for the edge either. And as far as edge storage costs concerned,
Okay, I've
so as far as edge storage costs are concerned, so let's say you have an upper limit on the edge storage costs, like that is being satisfied. So if you send a subset of data to the cloud, right, uh, uh, that does not exactly, what do you say, change anything about the edge storage, because anyway it is storing everything. Whether you send everything or whether you send half of it, it's not really going to be affecting the edge storage. Right? For example, if you have 10 megabytes of data that is sent to the edge, if you send 5 megabytes of it, still 10 megabytes will remain on the edge only. Right? It won't really affect the edge storage in any way. So what is the key factor influencing the performance of machine learning implementations on the edge in IoT systems? So is it A, cloud storage capacity, B, edge processor speed, C, specialized accelerators, or D, data transfer bandwidth? C, specialized accelerators. Any other responses? Yeah, edge processor speed. Okay, so there could be some sort of confusion between B and C. So now the edge processor speed, now it does influence, like it definitely does influence the performance of machine learning. Like there is no doubt about it. Uh, but if you see, like traditionally edge processors are not necessarily like by default equipped to do very intense processing, right? Very intense processing in terms of machine learning. Like it is only when like you add these accelerators, like let's say the neural compute stick, that actually enables these edge devices to be able to like do this kind of machine learning inferencing and all this. So so if you say, if you what which factor is influencing the performance of machine learning implementation, it is C. C would be like the most appropriate answer, because specialized accelerators are actually what is enabling these machine learning on the edge. And if you do multi correct, B would be like the second most appropriate answer. Okay, so A and D are not relevant, because see, data transfer is not totally relevant, because we do machine learning after the data has already been transferred, and after training has already happened. But in the case of cloud storage capacity, we're talking about the edge here, so it will not really affect. The edge is not exactly directly dependent on the cloud in most cases for doing inferencing. So you can create that dependency, but that has not been discussed, so I won't go into detail on that. So what is the purpose of purpose-built accelerators in chip design for IoT edge? So it is to slow down inferencing, to complement conventional CPUs, to decrease the speed of training, or to increase cloud storage. Okay. So I've seen B and C. So to someone answered C, decrease the speed of training. You want to decrease the speed of training? Okay, so I see two responses over here. One is to complement conventional.
B.
D, to increase cloud
No,
storage.
no, it's B.
B, to complement conventional
Yeah,
CPU.
to complement conventional CPU.
Yeah. Okay. So as far as this is concerned, so yes. So the answer is B, to complement conventional CPUs, and you cannot exactly decrease the. You do not actually want to install these purpose-built accelerators to decrease the speed of training, because there is no point decreasing the speed of training, and the only thing that you want to do is increase the speed of training, because that gives you better results in terms of you get to deliver insights faster, you get to build your applications faster. So, so the answer is to complement conventional CPUs. So purpose-built accelerators can be in the sense of like machine learning accelerators. So what role does the edge layer play in the IoT architecture discussed? Is it A? It primarily handles cloud computation, aggregates and filters data generated by sensors, foc- focuses on long term storage, excludes machine learning capabilities. B.
Option B.
Uh, any other responses?
A.
No, no. Abhirup, it, just see what role does the edge layer play?
So Edge is trying to mimic the cloud, right? Public cloud. So
Yeah,
it handles everything.
it handles it tries to mimic the public cloud, but it's not really handling what is in the cloud, right?
Oh, okay. I meant almost all features of clouds are in Edge. So
Hmm.
I thought that would be.
Okay, okay. So that would be I can understand your like line of thought. So but if even though it is trying to mimic the cloud, it is still not doing what is in the cloud, right? So in that sense, okay. So some of you have answered B. It aggregates and
B.
D.
Uh,
B.
yes, it's B.
Okay, okay. So B, it it aggregates and filters data generated by sensors, and so yes, so that is the correct answer. So we have already discussed this. So data that enters the edge, it aggregates it, it filters it, and then it does some kind of processing on it, and it does not focus on long term storage, because like this is more so suited to the cloud. Okay, because long term storage, see, there is no guarantee you will encounter the same end device again, and it also, for long term data storage, you need a very significant amount of hardware to do that. So that kind of thing is not really available at the edge, and it excludes machine learning capabilities. That is not true. We have seen this. You can deploy some sort of machine learning workload on the edge with the help of various cloud services. So, what advantage does machine learning on the edge offer in terms of data transfer to the cloud? So, is it well, we'll do this quickly. Is it A, decreased bandwidth usage, B, increased cloud storage, C, slower response time, D, limited filtering capabilities? So, any response is A? Okay, yeah. So, decreased bandwidth usage, that is correct. Okay, I think it is self-explanatory. So, machine learning on the edge offers uh, decreased bandwidth usage because you don't have to send too much to the cloud. So, what is the role of GPUs in the edge layer of an IoT system? So, does it A, handle cloud computation, B, minimize the use of specialized processes, C, assist CPUs in complex mathematical calculation for machine learning, or is it D, reduce the need for accelerators? C, any other responses?
C.
Mm-hmm.
Assisting CPUs.
Yeah. So yes, so C would be the most accurate answer. So as far as reducing the need for accelerators is concerned, uh, I can see that there may be some kind of confusion between the two. So let's say you have some sort of workload. So when you think of accelerator, don't only think of accelerators as in the context of machine learning, right? So you could create accelerators for all kinds of work, for different kinds of workloads as well. So if there is some sort of, let's say, so GPUs, I don't know if you're aware of this. So GPUs are very good at doing parallel processing. But let's say you want to do some sort of very specific kind of thing that you cannot really handle with parallel processing because of some sort of dependencies. you may need an accelerator that's very specific for that kind of task. So in that sense, it does not necessarily like always reduce the need for accelerator. But if you have some very specific kind of thing, then yes, it can reduce the need of accelerators. And does it minimize the use of specialized process? Once again, so the explanation for this B is actually an extension for the explanation of D, and of course, once again, the edge layer will not handle cloud computation. Okay, so which solutions facilitate the ability to take machine learning models trained in the cloud, perform hardware accelerated inference at the intelligent edge? So is it A, Azure Functions and IoT Hub, B, AWS Lambda and TensorFlow, C, Microsoft Azure IoT Edge Runtime, or is it D, Google Cloud IoT Core and Apache Kafka? Any responses? Some of you have said A. See, I want your answers to be like very specific, right? So Azure Functions, what is it for, right? So even I'm not fully aware of Azure Functions, but to me it sounds like it's for function as a service, right? That you had discussed in the first lecture. So hardware accelerated inference, right? Okay. So A and C.
C.
Okay, C. So A and C there is I can see. So you have, so at AWS Lambda it's, so I'll just explain this properly. So we need to be able to take machine learning models trained in the cloud and perform hardware accelerated inference, right? So if you want to take machine learning models trained in the cloud and we want to put them on the edge, we need some sort of service, right? So this is handled by the Azure IoT Edge runtime that was discussed in the previous lectures. And then after that, if you want to do hardware accelerated inference on it, so you need some sort of hardware on the edge, right? So IoT Hub, TensorFlow, and Apache Kafka. These are not hardware. These are not hardware exactly. So these are some sort of software that is written on the cloud to enable some sort of either device provisioning, device management. And TensorFlow is actually used to create machine learning models. Apache Kafka is used for data streaming. But on the other hand, Qualcomm neural processing SDK. So that is what is used to enable hardware accelerated inferencing. Okay, so I hope that is clear. So why is the training of machine learning models confined to the cloud or on-premise services or on-premise servers in IoT systems? Is it A, edge devices lack the capability for training? Is it B, cloud-based training is more effective, more cost-effective? C, it requires more resources like compute power and storage? D, edge devices have limited connectivity.
C.
Yeah. Okay, any other responses?
A.
Huh? A. Okay, fine. So, is it true that edge devices lack the capability for training? So, that is not exactly true, right? So, edge devices can do. Oh, just a second. So, edge devices are very much capable of training, but are they capable of training in the way that we want them to, right? So edge devices may not be able to take, let's say, a data set of, let's say, 2 to 3 million data points and do some sort of, and train a model based on it. So, but if you look at the cloud, right, the cloud has a huge amount of processing power and a huge amount of huge amount of processing power and a huge amount of storage. So because of that, what happens is uh, it becomes more capable of actually doing training on these training of these, what do you say, data. It is more capable of training the models based on the data. So that is why uh, it is more important. So that is why it is more capable. So thus the answer is C. Cloud-based training is more cost-effective. That is not always true. Uh, we have to look very closely into the cost to be able to determine that. All we know that it is more capable, right? Edge devices have limited connectivity. So now once the data has already been transferred, right? It is only after that we are concerned about training. So so that is why it is limited connectivity is not exactly that important a factor when it comes to training, because training, the process of training does not always involve some sort of data transfer over the network, unless you are in federated learning, then it all changes a little bit. But standard training, so what does inferencing on the edge in IoT systems enable? Is it A, increased cloud connectivity, B, real time data processing, C, dependence on the cloud, or D, centralized inferencing? A, B. Savi ma'am says B. Okay, any other? Okay, B, B. Okay, fine, fine. Yes. So yes, so B is the correct answer. So if you do, definitely if you do inferencing on the edge, right? So if you do inferencing on the edge, what happens is you can do you can process the data definitely in real time. Process the data that the sensor is generating in real time and give the insights and the actions back to the generate the insights and give the actions back to the actuators for actually performing the actions. So Stephen Raj has a question. You want to say something?
No, sir.
No? Okay.
Yes, sir. No.
Huh?
No, nothing, sir.
Okay, okay, fine, fine, fine. So dependence on cloud for all operations. Uh, of course, that is the exact opposite of this statement. So if you uh, if you actually do inferencing on the edge, you will decrease the dependence on the cloud. So obviously, it is a good thing to. Obviously, it is like more relevant to do real time data. The answer, the most relevant answer is real time data processing, and inferencing is not necessarily always centralized, because edge devices. I don't know if you remember. So in the first lecture we had discussed that in the first week we had discussed that edge is what makes the cloud truly distributed. So the inferencing may happen at any edge device, right? Edge device that the sensor is connected to. So it's not necessarily that the inferencing is always very centralized in nature. So in the machine learning process flow for IoT on the edge, what is the first step? Is it A, deploy the trained model, B, run the model on the edge, collect training data, or D, maintain the model?
C.
C, collect training. Sorry?
You have to collect the training data first.
Yes. That is true. I think this is very easy to answer. So if you remember the process, first you collect the training data, then you clean it, then you prepare it, then you train the model, then you do inferencing, then you get more data, you train the model further, you do more training, you do more inferencing, and then you increase the accuracy of the model. So obviously A is not the answer, because you cannot deploy the trained model before you collect the data, and you cannot run the model also before you deploy it, and you cannot maintain the model unless you deploy it either, and you cannot deploy the model unless you have collected training data. That is why C is the correct answer. So why is the process of collecting more training data and uploading it to the cloud important uh, in the machine learning process flow for IoT on the edge? So does it A?
It improves model accuracy over time.
Okay, any other responses? It has no impact on the model. It is a redundant step. It increases cloud storage. B. Okay, fine. So
Option B.
yes, so B is the correct answer. So if I had just asked you, why is the process of collecting more training data and uploading it to the cloud, like what impact does it have on the cloud, this process of collecting more training data? So it increases, well, okay, it does not exactly increase the storage capability, but it uses up more storage, right? So, so in that case, this is also wrong. And if I wanted to ask you why it's important, right, it improves the model accuracy over time. So that is true, but of course, like there are some more, there are a lot of nuances to this that have not been discussed in the course, but you can try to look at some topics like drift detection, and also there is a limit to how much, depending on a model, right, there's a limit to how much model accuracy can improve no matter how much data you feed into it, right? It's not like if you feed it infinite data, the accuracy will be 100%. So this is actually a very nuanced point. You need an understanding of machine learning to really be able to appreciate this 33B. Okay, so what is the significance of collecting historical data in the context of machine learning for IoT on the edge? So
C, enable seven hours fast data.
C, yes. Any other responses?
Option C.
Option C. Okay, so I'll just go over all the other options for the benefit of the other members in the course. So does it A, reduces cloud storage cost, B, it improves real-time data processing, it enables training models with past data, or D, it has no impact on the process? So does it reduce cloud storage? uh, yes, it does not exactly reduce cloud storage. You just if you collect historical data, what you'll be doing, you'll be using up more storage. And does it improve real time processing? So when it comes to real time data processing, all this step is only relevant after the model has already been trained and developed, right? But if you look at the next step, right, collecting historical data, after that you will do the whatever data cleaning and processing. So because of that, it will enable training, right? So there is no real direct link with this B, right? If you want to improve real-time data processing, you need to either make the model faster, or you need to make the hardware faster, you need to improve the situation of the hardware. So if you see it, if you collect historical data, you can train models with the past data. Okay, you need not always you need not always depend on like the real-time sensor data. Okay, so D, it has no impact on the process. That is not true. Of course, if you have historical data, you can do more training. So why is raw data collected from devices and sensors and not directly usable for machine learning? Is it A, it lacks historical context, B, it requires additional storage, C,
Senses.
C.
C. Okay. C, it needs data cleanup and preparation, D, it is already formatted for machine learning. C. Okay. Any other responses? No? Okay, fine. So yes, so C, it needs data cleanup and preparation is the correct answer. So it requires additional storage. So that is not true. Like data collected specifically from devices and sensors is not really special in the sense that it requires additional storage. It requires like the standard amount of storage, right, that is allocated to getting data from devices. You may be able to reduce the size of the data in some way because of the processing, but that is somewhat nuanced. We haven't discussed this exactly. C would be the most accurate answer, as far as it lacks historical context, that's not true. You can also train data for machine learning that does not have any historical context either, any like significant historical context. So historical context is like somewhat relevant when it comes to like time series data. But let's say you want to train like a machine learning model that that wants to in which you want to tell the difference between cats and dogs. You don't need some kind of historical data like what is the definition of a what kind of images were there in like the history, right? So this is somewhat relevant when it comes to like time series data, and obviously D is not the right answer because all this data need not already be formatted for machine learning. So the data may not already be formatted for machine learning when it comes like directly into nature, right? So these kind of you may want, for example, let's say you have words, you may want to convert these words into numbers using some sort of encoding techniques with the help of some sort of embeddings using, let's say, like some sort of transformer model. So that would be one example. So of course this is also same question. What might be involved in the data preparation step for machine learning in the IoT scenarios? Is it A, reducing data storage, B, increasing raw data complexity? Is it
B.
sorry, B, or C, data C, data reformatting and cleanup, or is it D, ignoring historical data? Okay, before I
C, sir, C.
C, okay. Yes, so C is the correct answer.
This is C, sir.
C, okay. Yes, so C is the correct answer. So what it does, so what it enables is, it reduces data storage, increases. It doesn't exactly reduce data storage. It does not increase the raw data complexity. So in data preparation step, what you want to do is you want to format the data in such a way that, and you want to clean the data in such a way that the ML model can take it. So cleaning up, some examples of cleaning up may mean, let's say you have some sort of text data, you may want to do something called normalization on it. So for example, you may want to remove the full stops, or you may want to remove the dots, let's say after an abbreviation like doctor, you may want to remove the dot after doctor. So, or you may want to, let's say the text is multi-space between words, you may want to convert it to single space so that your model can understand what is happening. So since I'm in natural language processing, so these are some examples of that. And yes, and ignoring historical data, of course if we have historical data, we don't always want to ignore it. We want to try our best to include it in our data sets. So what role does a domain expert play in the data preparation step for machine learning in IoT scenarios? Is it A, collecting the raw data, B, pre-processing data, C, injecting additional information, or D, creating explicit labels?
So B or D, sir?
D,
B is the pre-processing.
pre-processing. So no. See, so by pre-processing you can already write into the edge, right? You can already write
D.
What is it? D, sir? D.
D. Okay.
Option D, sir.
D.
Yes.
Okay. I'll go over the options one by one and try to explain to you what is the correct answer. So let's say you have a real-time some sort of IoT scenario, right? Okay, you want to collect raw data. So of course, if you have a domain expert, right? Like if you have a data scientist, let's say a data scientist specifically, a data scientist can do all these four. But a domain expert, right? For example, let's say you have something very specific, let's say in fire alarms, right? You want a domain expert to tell you whether the fire alarm is, let's say you want a domain expert to tell you whether, let's say, some sort of temperature is more likely to occur in the case of a fire. So he may not have that kind of data science knowledge of collecting raw data and pre-processing data. right? Or as far as injecting additional information is concerned, that is very vague. Okay, so we don't know what kind of additional information they will do. But as far as D is concerned, 37D, creating explicit labels for data points, that is relevant. So because we want a domain expert to tell us what this data means, and after the domain expert tells us what the data means, we want to send this data to a machine learning model, so that the machine learning model can extract some sort of hidden rules inside what the domain expert is saying, right? So that is why the domain expert is relevant. So before so one thing I want to ask you: were you all able to like really appreciate or understand the convolutional neural networks that were discussed in the object detection part of the course? I just wanted to ask you this question. Yes.
Yeah. Yes.
Okay. So did you all already have a background in CNNs, in machine learning, or did you have to like learn it on your own?
Need to learn around.
Okay. Fine. So if you have any doubts related to that, see, my field of work is actually in neural networks. So if you want like some fundamental, like if you have some doubts about neural networks, you can ask me. Okay. So but I won't be. You don't need to know like the inside architecture of what YOLO and SSD is doing in that much depth actually. But if you want some basic understanding of how neural networks work, and the basic algorithms for training neural networks, like I can answer those kind of questions because my PhD area is actually in this. Okay. So what is the information provided by? Let's go to question 38. What is the information provided by domain experts and data scientists allow machine learning algorithms to find during the data preparation process? This is also like I have restated the previous question in another way, but this is also like somewhat relevant. You should have an understanding of this. Is it A, data storage patterns? Is it B, correlation between sensor data and expected results? Is it C, historical data context? Or is it D, reduction in raw data complexity?
These were correlation between sensor data and expectations.
Any other B? Any other responses?
It's B.
B? Okay, fine. So ma'am, I'll just mute you. Okay. So previously what we had discussed was we need these domain experts to tell us what the data means, so that a machine learning model can extract the hidden rules. So another way of figuring, so now what that fundamentally does is it creates correlations between sensor data and expected results, right? So the information provided by domain experts and data scientists, so what does it allow machine learning algorithms to find? So it allows them to find correlations between sensor data and expected results. So if you have some sort of sensor data, and if you want to figure out what a group of those sensor data means, you can do it using this. You can figure it out using, what do you say? You can kind of figure out what the relationship between sensor data and expected results is with the help of these domain experts. And so now the information provided by them, it does not reduce the raw data complexity. If you want to do that, you need to do some sort of pre-processing. And historical data context, it is vague, but this historical data context may lead to finding correlation between sensor data and expected results. Data storage patterns is also something that is in a very specific case. So if you are studying data storage patterns, only then they will be interested in finding these out for you. But in general, let's say data storage patterns is not relevant to you, then A would be the wrong answer. But the most accurate answer in this would be B. Okay. So what does building a machine learning model involve in the context of IoT data processing? data storage patterns, data cleanup, ignoring historical data, or experimenting with different algorithms and parameters. Okay, fine.
C.
C. Okay. Yes. So C is the correct answer. A lot of you have answered C. So, experimenting with different algorithms and parameters is actually how you is actually the involved is actually what you really need to do in the case of machine learning. So I don't know if you are aware of this. So fundamentally, what all of these different algorithms and parameters do is like they try to find different techniques of learning patterns within the data, right? So a different technique may max out at a different accuracy. Another technique may max out at a different accuracy. So and even within the same algorithm, if you give it different parameters, right, you will get different accuracies. And also even how much time you train, even for how long you want to train the machine learning model, even that can also have an impact on how much accuracy or like whatever metric you're using for measuring, you know, or whatever metric that you're using to measure the performance of the model. All of these can be affected.
Hyperparameters.
Yeah, so like
Do you like
hyperparameters, that is more relevant if you have like neural networks, right? But if you want to like say generally across,
a- something RBF or anything? Those are hyperparameters. Parameters are the output of the model. So
no, no,
hyperparameters are the inputs we define, and parameters are the say any regression model ABC after it runs, that those are called the parameters actually. So did you mean hyperparameters, the input to the model, or the out
no, no. So
input to the model includes like we are setting, for example, in neural networks, number of layers and per layer, how many neurons. Those are the input parameters. Those are what I remember. Those are called hyperparameters, and the output models calculated value according to the trained data set. That those are called the parameters. It, so is my understanding correct?
okay,
For
so
example, in SVM, if we give Gaussian RBF and not linear, so those are called hyperparameters.
yes, yes. I get what you're saying. Yes, yes. So okay. Uh, what do you say? Okay, so I think so for the benefit of the for the remainder of the class, the hyperparameters basically what you can control, and parameters is like the weights, right? That you can learn in real
Yeah,
time,
correct.
right? Okay,
So
okay.
that's the output of the train.
So like I wouldn't exactly say that is the output, but like it is like in the process, right? In the process
Yeah,
of
yeah,
training the model. Yeah,
weights.
Like for example, if I have a neural network, I am not, and I'm an end user. I'm not really concerned with the weights, right? I am more concerned with like I'm not really concerned with the weights. Like I am more
Yeah.
concerned with like what is there in the final layer of the neural network, right? So okay, so you are right. So experimenting with different algorithms and hyperparameters. In that sense, yes. Okay, so yeah, so that thank you for pointing that out. But the thing is, like this is kind of like an introductory course to like cloud edge ML. So they like hyperparameters and parameters are not exactly interchangeable. Okay,
Yeah.
so we cannot really say that yeah, a parameter is hyperparameter, but you know, but yeah. So you would be you are right when you say hyperparameter should come here. Uh, but but for now, uh, but like for a layman, right? You can call hyperparameters also like parameters for a layman.
Yeah. Okay.
So I hope that like wasn't confusing for other people, but fundamentally, so what Abhirup was saying was, let's say you had looked at like support vector machines, right? Or okay, is there some machine learning model you have looked at? Okay, so you have looked at, huh?
Regression model also.
Huh,
How much degree?
Yeah,
means
yeah.
x square cube up till what degree that
Ha, ha,
we
ha.
need to do.
So yeah, so if you're doing polynomial feature transformation, then yes, but I don't know if it has been discussed in the class. So okay, so you have discussed like convolutional neural networks, right? Okay, so in convolutional neural networks, like because of fast CNN, fast RCNN, faster RCNN. Um, so in that you must have seen that there are like several layers. Okay. So I'll tell you. So you have you have like a certain bunch of layers in the convolutional neural network. So Abhirup had pointed out that if you were to describe like how many layers in the convolutional neural network, so that would kind of fall under like the hyperparameters. But within a convolutional neural network, there are some weights that you want to train, right? So at different stages, like there's a feature map, and in that feature map, like there are some weights corresponding to it. So like the you want to train some weights. Uh, so you want to train some weights when it comes to each layer. So those kind of weights that are in between, those are what you call the parameters, right? So so what you can control as a hyperparameter, but what the model controls is the parameter, right? So if you experiment, when it comes to experimentation, that is what you do, okay? And when it comes to experimentation, that is what you do. So you can only play with the hyperparameters. I hope that was clear. Okay. So what is the immediate step after building and training a machine learning model in the IoT context? Is it A?
B.
So is it A? Okay, data storage pattern. B, model deployment on IoT edge. Is it C, data cleanup, or is it D, raw data extraction? Uh, okay, you have said B.
Model deployment on IoT.
Sorry,
Model deployment on IoT.
model deployment on IoT edge. Okay. Yes. So B is the correct answer. Um, yes. So after you build the model and after you have trained it, so so building means you have written the code for it, and training means you have as training means the parameters of the model have come to some sort of optimal value because of some sort of algorithm. So I, so so then after that has been achieved, then you do the deployment of the model on the IoT edge, right? So data cleanup and raw data extraction and data storage patterns. So all of these things actually happen. Sorry, data cleanup and raw data extraction. All this happened before training. Data storage patterns, that is irrelevant to this question. So after deploying the model on an IoT edge, what can the system achieve in terms of predictions? So predictions can only be made in the cloud. Predictions are not possible.
Answer C.
Option C.
Okay.
Predictions can be made locally on the edge.
Yeah, predictions can be made locally on the edge device. Predictions require separate server. So yes, so that is the correct answer. Um, predictions can be made locally on the edge device. So because if you deploy a model on the edge, then you can do predictions on it. I will go to the next chapter because of shortage of time.
Yeah, it's C.
Yeah, see it. Okay. We were at 41, right? Okay. So what is a so we'll go to the next one, which is ML based image classifier at IoT edge. So what is a crucial step in training a computer vision machine learning model? Is it extracting features from images, applying complex math, identifying background?
D.
Answer A, sir.
Answer?
A. Extracting features from images.
Yeah. So it is a crucial step. So in the process of doing A, you might have to do B, and and there are many techniques. There are some techniques that you can use to extract features from the features from images, and as far as mimicking human understanding. So uh, that is the overall goal of the entire computer vision process. But what we fundamentally do is we want to extract features from images so that we can so that it can be possible to train uh, so that it can be possible to train the, what do you say, model.
Train the models,
Yeah.
learning models.
So by features, what do you mean? Like, is it pixels you're talking about?
No. So
If vectorize the image or something, like extracting features means what? Is features attributes out here, as in
yeah,
vector?
so there are some properties of the images, right? So for example, you can detect the edges in the image, and you can do some kind of uh, you can figure out where the edges of the image are, and you can pass that into the model. That could be one example of a feature. After that, so what can you do? You can probably figure out some sort of gradient in the lighting in the image. You can pass that to the model for inferencing. So whatever the key properties of the image, right? Those are the features.
So I wanted to know,
Yeah.
image can be typically broken down, say any 200 plus 200 image can be broken down into, say, pixels, right?
Yeah.
There are total 200 and if it's a black and white picture, so 200 into 200, that many number of pixels.
Yeah.
So each will contain, say, 0 to 255 value, correct?
Yeah.
For a black and white. So typically, when we give an image to any model, we usually convert it into a vector and then feed it. So whatever features are you
See
telling,
that.
are these
See,
values of these pixels or something else?
see.
Because
That,
yeah,
that depends on the
yes.
model, right? See, if you have, let's say, some sort of deep learning model, then what you can do is you can stack up all the pixels one by one like this. Like, let's say pixel data here, pixel, and you can pass it into the convolutional neural network. And then after that, at every step, it will learn some feature. Okay. See, a feature is always some important property of the image, important property of the data always. Okay, if you consider the the pixel intensity at every coordinate property, that is also fine, but that is not the only way to figure out the features of see
Can you give
whatever.
me some examples, like what can be the other features of an image?
Yeah, so the
I'm not
edges,
getting,
right?
because all information in an image can be vectorized
See,
in
if
the format I'm telling you, like the converting into pixel data basically. So I
yeah,
wanted
yeah.
to understand
See,
what was.
fundamentally, right? Any important pattern that is in the data, right, can constitute a feature. So I hope that is any if there's any in the data, right? If there is some sort of pattern you find, right, that is somewhat important, and you think you can use that to be able to do inferencing or training easily, then that you can call that a feature. So for example, like let's say you see my face over here, right? You can I using, let's say, some sort of Fourier transform, I am able to figure out where the boundaries of, let's say, my face and this outside and whatever the white background is, right? You can pass this kind of data into the model, and the model will be able to figure out whether this person is Rachit or Abhirup, right? So for example, that's what you think I can, let's see if I can bring up an image of something. Mm. Okay, one thing, even the bounding boxes, right? Like that can also be a feature. Can you can see, you can pass this kind of thing, right? See, let's say you have a machine learning model. You don't have to pass everything pixel by pixel. Okay, like you can pass this kind of, you can do some sort of pre-processing. In the pre-processing you can figure out these edges, and you can pass this edge data into the model itself. Is it clear?
Okay.
So you don't always have to just pass every pixel, what is there in every pixel. You can do some sort of processing, figure out what is the important characteristics of that image, you can pass that into the model. Okay, anyway, if you see the neural network, right, if you do see the neural network, if you have multiple layers, at every layer it will do some sort of, it will try to figure out something like this. So I hope I'm clear. Is there anything else you want to ask? So what is the purpose of, okay, the same thing. What is the purpose of feature extraction in computer vision? Is it A, identifying animals, B, recognizing background objects, C, applying complex math, or D, understanding the key properties of objects?
So D say
Huh?
D.
D, understanding key properties of the objects.
D.
Yes, so that is, yes, I just discussed the main properties of the main properties of the image. You have to pass that into the to figure out things. Or okay, I'll just do one more Google search for you. Yeah, so you can, so color, you can pass texture and shape features also, like this feature extraction. I think Abhirup was asking about this. I don't have like a deep knowledge of image features actually, because I'm in natural language. But if you were asking about like natural language, I would have a better answer. Yeah, see, so if you see here, features include properties like corners, edges, regions of interest, points. So these kind of things are, some sort of, these kind of things are also you could pass into a machine learning model.
Okay, now.
Okay.
Okay. Now, the type of programming I had done was a bit like it used to take full pixel info, so I'm not being, means I don't have too much background, but whatever, like I cannot currently fathom how will we have some particular, for example, the way I was telling that captures the entire image specification. So I'll try to research a bit.
Okay. So I think, see, that kind of depends also on your use case, right? So let's say for some kind of use cases, let's say color is not important, right? Then you don't need to even then you don't need to like worry that much about the intensity and all. You just need to, let's say you want to do like object detection, right? So in that case, color may not be that important. So in that case, you may just want to like get away with the edges. So you don't have to pass all the pixel data of the entire image into the machine learning model. So that kind of thing is. Okay, so what is crucial to determine the performance of a machine learning model? Is it A, advanced algorithms? Is it B, model complexity? Is it C, domain expertise? Is it D, quality of the data set?
Quality of the data sets.
Yeah, so it is crucial, right? So model complexity is also important, but like whether that is also crucial if you really ask me. Okay, but once again, it depends on the situation. So if you have let's say a very complex use case, not complex use case, let's say if you have a lot of data, right, and there are like many patterns that you want to learn, then the complexity may be like somewhat important, right? And then you may need to like have a more complex model. Like it depends on the use case and domain expertise. So that will impact the quality of the data set, and based on that you'll be able to figure out, yeah, based on the quality of the based on the domain expertise you'll be able to figure out the quality of the data set, and that will impact the machine learning model's performance. So in that case the direct answer would be quality of the data set. Advanced algorithm, that is somewhat vague, so it is not the right answer. So what is the primary objective? So what is the primary objective in computer vision when dealing with images and videos containing pixels?
Answer C, sir.
Yes. So is it extracting audio? This is also simple. I won't go into too much depth in this, but fundamentally, if you go over like all the goals in like what is common across the goals in computer vision is you want to recognize objects or patterns in the image, the way a human being would. So what does image classification in computer vision refer to? Is it A, locating objects in an image, B, assigning labels to objects in an image,
C.
enhancing image resolution, or D, converting? C, enhancing image resolution,
Yes, sir. Answer A.
locating objects. Is it D, converting images to videos? Sorry?
Image classification is like dog or cat we are doing. So labels.
Yes.
Labels.
Hmm. Yes, so B is the correct answer. It assigns labels to objects in an image. So now let's just, sorry?
Sir, can you discuss some questions on object models?
Object models as in? Oh, as in fast RCNN and all?
Yes, sir. YOLO.
Wait. Okay, fine. I'll just get to them. Okay, how about this? Like, next time, like, can you all just send me requests on where you want to see questions, and I'll make from there only. I actually have some questions on that. Okay, fine. Let's start here. I don't have too many questions on that, but okay. This one is okay. Let's start here.
Region-based.
What does RCNN stand for in computer vision?
Region-based permission.
Option B.
Option B. So, what are the three main steps in the RCNN approach for object detection? Is it A, feature extraction? B, is it A, feature extraction, region classification, bounding box regression? B, convolutional neural network, support vector machine, K means clustering. C, selective search, convolutional neural network, linear regressor. Or D, object segmentation, image classification, pattern
Answer
recognition.
C, sir.
C. Okay. Any other responses? Okay, I'll do one thing. Like I'll just put my email here. If you want me to discuss like from some very specific area in the text, just email me this like maybe today or tomorrow, or like in the session, so that I can prepare for that. Okay. So the answer here is, so in the RCNN approach, what happens, right? So you first find the region proposals. Then for each region proposal, you apply one convolutional neural network. And then after you apply the convolutional neural network, then you want to find the coordinates of the bounding box where the object may be located. So finding the coordinates of the bounding box is actually a regression task. So this is achieved with the help of a linear regressor. So in that sense, C would be the most accurate answer. And after that, convolutional neural network, the other options are not exactly correct answers, because feature extraction, like all this, like it's a very general term once again. Now regional classification, that happens at the end, and bounding box regression also happens along with region classification. One second. Let's just go back 1 minute. And B is also the wrong answer because there's K means clustering. So clustering is actually an unsupervised technique. So unsupervised techniques, you don't need a domain expert to do some sort of labeling. We try to learn classes just given the data itself. We try to find some structure in the data directly. That's why B is the wrong answer. As far as D is concerned, object segmentation, image classification, pattern detection, this is very general. This is true for all kinds of image classification, computer vision tasks. So why is RCNN considered slow in practice? Does it A, it lacks a convolutional neural network. B, it requires manual feature engineering. C, it involves an initial step of identifying. Sorry? Yeah. Yes. So there is a selective search. Okay, sir, can you explain in brief about working and difference of fast RCNN, faster RCNN, and YOLO at the end of session? Okay, sure. Fine. YOLO, I am not very confident, honestly. You can just look at the lecture slide, but this faster RCNN, fast RCNN, definitely I will explain. Okay, so YOLO, because see, it was not discussed in too much depth in the lectures. I don't want to say something that that may not be fully relevant to you all. Okay, and also not fully clear on this YOLO. Okay, so so it involves an initial step of identifying regions of interest. That is the main problem. So what is the challenge in terms of duplicacy faced by the RCNN model when an image contains multiple objects? So is it A, multiple CNNs need to be run for each object? Is it B, overfitting of the CNN? C, lack of region proposals, or D, insufficient training data? Anyone has any responses? Hello?
B.
D, insufficient training data.
Yes, sir.
C, sir. C.
Lack of region proposals. So where there's no lack of region proposals, right? In the RCNN, we want to create as many we want to create region proposals, multiple region proposals that we pass in the. Yeah. So A is the correct answer. So multiple CNNs need to be run for each object. That is true. So in the context of RCNN, what is the purpose of the support vector machine classifier? Does it do?
Classification.
Sorry?
Answer B. Object classification.
Yes. So the support vector machine, it is a classifier. Okay. So the support vector machine, what it does, it draws a hyperplane between two classes, between data points belonging to two classes, effectively separating them. So does it A, region proposal generation, B, object classification, C, feature extraction? So it does not do any feature extraction. It is a machine learning method. So it needs to feed the features into the classifier, and it does not do bounding box regression. Bounding box regression is handled by a linear regressor. So the answer is B, object classification. So what role does the regressor play in the RCNN model? Does it A, generate region proposals? Does it B, classify objects? C, extract features? D, determine the coordinates of object bounding boxes?
Answer B, sir.
Yes. Answer is D. It determines the coordinates of the object bounding boxes, and it does not generate region proposals. That is already done by the algorithm itself. And classifying objects, that is done by the SVM. Extracting features, that is done before training. That is done during in the process of training at each layer in the CNN. So what was one bottleneck addressed by the fast RCNN in comparison to the original RCNN? Does it do A, slow object classification, B slow feature.
D.
Yeah. So slow region proposal. No, wait, 1 minute. Sorry. Yeah.
Too
So
many CNN.
yeah. Right. So what was one bottleneck address? So the fast RCNN, it uses only one neural network in comparison to the RCNN, which used one convolutional neural network for each region proposal. So, but this problem of slow region proposal generation is still there in the fast RCNN, because you are generating the region proposal generation, the region proposals from the feature maps, from the final feature map at the end of the layer using some sort of algorithm. So C is still a problem. Slow feature extraction, that is vague, we don't know that for sure. Object classification, of course, if the entire process is slow, this will also be slow, but that is still vague. Okay. So what is the bottleneck in the fast RCNN model that led to the introduction of the faster RCNN model? Is it A, slow object classification, B, inefficient region proposal generation, C, limited feature extraction, D, lack of fully connected layers?
B.
B? Yes. Any other responses? Okay, fine. So B is the right answer. So because of the inefficient region proposal generation, we created something called the region proposal network. So because of what that assisted in was that kind of made it more efficient, and yes. So but obviously the algorithm that was used to generate the region proposals has not been discussed in the lecture. So you don't have a full understanding of why exactly RPNs were faster than this, but you have to take the instructor's word for it for now. So how does the region proposal network generate multiple possible regions for each sliding window location?
So what is the answer for the previous question, sir?
Oh, so for 73 the answer is B. Inefficient region proposal generation.
Okay.
Okay, so these are like very direct questions. Not see the main intention of these questions is just so that you get some sort of revision of the lectures. You can like think about it critically. If you want like harder questions, I can like try to bring that in also. So how does the region proposal network generate multiple possible regions for each sliding window location? So this is answer is in the question, but still.
Answer C.
Yeah. So yes. So what it does is, uh, it by using a fully connected layer, applying a pooling layer, sliding the window across the feature map, by using a regression layer. So yes. So that is true. The answer is C. Um, so if you slide the window across the feature map, you create k anchor boxes. Each of those anchor boxes will correspond to a region proposal. Okay, so what is the intersection over union measure in object detection models? So A, area of the predicted bounding box.
Answer B, sir.
Answer?
B.
Exactly,
Answer
B, right? Okay, fine.
Yes, sir.
Yes, so B, overlapping area between predicted and ground truth bounding boxes. C, the number of bounding boxes. Versus D, total area. Yes, so the answer is B. So intersection over union, what it does is it takes multiple. So it takes the ground truth box and it takes the predicted box. It finds the overlapping area. So let's say the overlapping area, let's say 10 pixels, and then let's say if you take the union of both those bounding boxes, you get let's say an area of 30. So the intersection over union will be like 10 divided by 30 pixels, so 1 by 3. So how is the intersection over union value interpreted in object detection? So higher IOU indicates better performance. Higher, yeah. Yeah, IOU is not relevant for object detection. A lower IOU gives better performance. IOU measures the total area covered by the bounding boxes. So yes, so a higher IOU, right? So, so what happens if you have a higher IOU? So it means there's a higher intersection, right, between them, and there's a smaller union. So what happens when there's a smaller union? So see when we have two bounding boxes, right, and we want to make sure that they are perfectly overlapping. We want to make sure that, see, if they are two very far apart, then these two have a very high union, because the union between these, let's say my hands are the two bounding boxes, right, A and B, right. So if I want to find the union between these two bounding boxes, it is literally A plus B, right. Then this will be the union. But if I slowly overlap them a little bit, what will happen is, it will be the union. If you want to calculate the union between these two bounding boxes, it becomes A plus B minus this intersecting area, right. So this is a situation of high accuracy in comparison to this. So in this, because of the intersection over here, right, because of this intersection, there is a smaller union. So the more you increase the intersection, the smaller the union becomes. Okay, and the more you increase the intersection, the higher the numerator becomes. Right. So if you have a high numerator, which is in the case of high accuracy, and if you have a low numerator because of the high amount of bounding, you will get a higher intersection over union value. So in which case you have a more ideal case in terms of object detection. Okay. So a certain performance metric is given by TP divided by TP plus Fn, where TP represents the true positives and Fn represents the false negatives. Yes, so this is recall. So F1 score is actually, so precision is basically true positives divided by true positive plus false positive, and F1 score is basically the harmonic mean of recall and precision, and accuracy is what you get when you just sum up the true positive plus the true negatives divided by the true positive plus true negative plus false positive plus false negatives. That's what gives you the accuracy. Basically everything correct divided by everything. Okay, so it's 5 o'clock. Someone had asked me to explain the differences between the functioning of these two. So I will just let me see if I can explain this in some detail. So Dave had asked about this, right? I'll just go into those slides and see if I can explain this. Okay, I haven't asked too many questions from custom vision. Okay, so let's start with standard RCNN, right? So what I'll just see what all she has asked. Fast RCNN and faster RCNN. Okay, only these two he wants. Okay, so fast RCNN. So what happens is, so let's say I have an input image, right? So do you know what the architecture of a convolutional neural network looks like, right? I'll take one example. So the AlexNet is actually a convolutional neural network. So okay, so let's take this example. So what you will do is, I hope this is visible. Okay, I'll just go back once. Fine. So can you all see this image? You all see this AlexNet architecture, right? So what happens in this AlexNet is, so first you take an image, you will pass it through this through these convolutional layers. The convolutional layers is basically it will take a kernel. So kernel is like a matrix, not a matrix. A kernel basically it is like a grid of numbers. It will multiply the pixels with those numbers and it will like add them up. Okay, it will do it like over multiple layers, And then after that, at the end, you have something called a fully connected layer. So whatever is the output of this fully connected layer, of this convolutional layer, it is passed into this fully connected layer. And then after that, whatever is at the final layer, what happens is you get something called a feature map. The output of the final layer is called a feature map, right? So so over here you have like a simple convolutional neural network over here. So then what happens is, after that, you get this pooling layer, you get this feature map. After that, the regions of interest are gained. Okay, so this regions of interest, you use some kind of technique. We don't know, that technique has not been discussed over here. Okay, so after this technique, right, it will generate the proposals in terms of bounding boxes, right? So these bounding boxes are actually passed into what is called an ROI pooling layer. So what you do in an ROI pooling layer is, so the thing is, the region of interest may be different for different kinds of different kinds of, basically the regions of interest may be of different sizes. In order to bring them to like some sort of like common size, you pass them to a ROI pooling layer. Then after that, you pass through fully connected layer, and then now the linear plus the softmax layer will do the classification, and the linear layer, the standard linear layer will act as the regressor to find the bounding boxes. Okay, so what a softmax does is, it will take the logits. So what the logits are, it is basically the output of the in the final layer of the linear layer, and then it will convert it to like something called a probability distribution. In a probability distribution, it will make sure that all the outputs sum up to 1, and all the outputs are less than 1. Okay, so you can find maybe the maximum of that, and that will with that you can classify whatever is in the bounding box into an image. So basically the main idea is, after you create convolutional neural network, you get a feature map, and from the feature map you generate region of interest, and from the region of interest you are able to do something called you're able to create the classifier, and you're able to do bounding box. So as far as faster RCNN is concerned, so from the feature map, okay, you create something called a region you use something called a region proposal network. So instead of this instead of a proposal method, you use something called a region proposal network. How does this region proposal network work? So what you do is you pass a 3x3 sliding window. Okay, so let's see, there's some notes app online, then I can explain with that. Okay, so I'll just create one more slide actually. So a 3x3 sliding window, so it can be of like this size. Okay, so a 3x3 sliding window will kind of look like this. It has like some three, so like let's say this is your image. On top of this you can it will go 3x3 at a time. So if this is the pixel data of your image, it will take this, and it will generate some anchor points. So it will generate some anchors based on this. It will generate some anchors that is centered on, let's say, this 5, and it will create and then after that it will create some anchor boxes. So basically just like standard boxes that is based on this, whatever is the output of this 3 thing, and then those anchor boxes will act as like these bounding boxes that you get from these anchor boxes will act as like region proposals. Okay, then these region like that's what I think. I may be wrong. If I'm wrong, you can like point it out. And then after that, each region proposal, you get a score associated with that region proposal from the neural network, right? So basically, there's a sliding window. From that sliding window, you generate some anchor boxes, and then from those anchor boxes, you will assign an object score and the bounding box, instead of using some sort of proposal based technique. Okay, so this anchor box so this anchor box can be of like it has to be fixed, right? It has to be fixed ratio, but a fixed ratio as in it can be like some 2 by 2 or like 1 by 1, but you can create as many of these as you want. Okay. YOLO, well, I won't really go into like too much detail, because it has not been discussed in that much detail in class actually. Okay, so but basically the main idea is, instead of selecting some regions, it will approach object detection problem, like basically it will what it will do is like it will like forward the entire image. Okay, instead of like selecting some regions. Okay, instead of like creating some sort of regions and doing something, it will forward the entire image to predict the bounding boxes. Okay, instead of, let's say, like creating some sort of bounding box and then doing all this, and then doing like classification loss, bounding regression loss, and all this. So I hope that's clear. Okay, and actually, if I had prepared a little bit more, I would have been able to explain the YOLO V3 in detail. Okay, but I'm sorry, but I hope you get the main idea, right? Wait, let me see if I can show you what anchor boxes look like. Because the idea of anchor boxes may not be like directly clear, just seeing the okay, so like these kind of, you could say like these so with respect to like every sliding window, you can have like an anchor box like this. Okay, so like inside anchor box you can do some kind of prediction. Okay, I think you can take a look at this link. This link is a good link to understand what anchor boxes are. Okay, so okay, fine. So I think this brings us to the end of the session. Okay, thank you. Thank you for coming. And if needed, you can contact me on this email. Right now, I'm not like fully clear on how to explain anchor boxes to you, but yeah, I will try my best.
Okay.
You can.
Thanks, Rajat.
Thank you, sir.
Okay, thank you.
Thank you.
Mm-hmm.